Hello everyone, welcome to mathematics class. This lecture is exclusively recorded for second year BSc student of BK Birla College, Kalyan. This is calculus paper, mathematics paper 1. In this lecture, we will define the differentiability of scalar valued function, and there are two results related to that differentiability we will prove. So let me define differentiability for a vector valued function. So let f is from u subset of Rn to Rm, where m is greater than 1, be a vector valued function defined on open set u subset of Rn. Let p belongs to u. We say f is differentiable at p if there exists a linear transformation T from Rn to Rm such that limit of h goes to 0, norm of f of p plus h minus f of p minus t of h norm complete upon norm h. This should go to 0. And t is called as the total derivative of f at p, and it is denoted by dfp or f dash at p. There is another definition in terms of error function. So let f is from u subset of Rn to Rm, where m is greater than 1, is a vector valued function. U is open set in U in Rn. Then f is said to be differentiable at p belongs to U if and only if there exists a linear transformation T from Rn to Rm and error function E from Rn to Rm such that f of p plus h minus f of p is equal to t of h plus e of h, where this e of h, where limit of h goes to 0, norm u of h upon norm h, this should go to 0. Okay, so let's have a theorem related to differentiability. So theorem is as follows. Let f is from u subset of Rn to Rm. Here m is greater than 1, given by f of x is equal to f1x f2x dot 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 fmx, and here x is equal to, basically it belongs to Rn, so it is x1 x2, it will have n component xn which belongs to u subset of Rn. Let p equal to p1 p2 dot 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 pn which belongs to u subset of Rn, such that f is differentiable. Instead of such that, I'll say then f is differentiable at p if and only if each fi is differentiable at p. So this entire f is differentiable only if and only if each component, that f1 f2 dot 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 fm, so each fi should be differentiable at p. So the statement is if and only if. So the converse part, if each fi is differentiable, then we can say that the tuple function, that m tuple f1 f2 fm, that function is also differentiable. So in a problem solving, if somebody give you a differentiable vector valued function, and if somebody asks you to check whether it is differentiable or not, one of the way is to check whether each component is differentiable or not. So if each component of f is differentiable, implies that function is differentiable. So let's prove this. Proof is not difficult. It is just you need to use the definition in a proper way and some of the rules of norm. Okay, so it is given that f is differentiable at p. So this would imply there exists a linear transformation T from Rn to Rm such that limit as h goes to 0 f of p plus h minus f of p minus t of h, this everything should be in norm, upon norm h, this should go to 0. Here note that t is a function from Rn to Rm, so t is basically has m component, t1 t2 dot 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 tm, and each ti here is a linear transformation, so each ti is lt, that should be noted. Okay, so if this is equal to 0, then let me write down f in a, expand this in a correct way. So this is if, so this theorem is converse, means we have to do if and only if. So reverse, if you go in a reverse steps also, then we will get the same proof. So limit as h goes to 0, norm of, now here it is f of p plus h, so it is f1 p plus h comma f2 p plus h comma dot 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 fm p plus h. This vector, first of all, bracket complete, minus f of p minus f1p f2p dot fmp. This bracket should not come, minus t1h comma t2h dot tmh. Now this bracket complete, this whole norm divided by norm h. This is if and only if limit as h goes to 0. Now what I'll do, I'll write in a proper way. So it is f1 p1h minus f1 at p minus t1 at h, okay, upon comma. What I'll do, one more thing I will do, I will multiply here, it is norm h, and here I will multiply and divide by norm h to every term. So norm h, comma. The second term will be f2 p plus h minus f2p minus t2p upon norm h into full term we will multiply by norm h dot. The mth term will be fm p plus h minus fm minus fm at p minus tm at p upon norm h into norm h, and this whole norm will get completes here divided by norm h. Now what we will do, this norm h, this norm h, so this norm h and this norm h, this all norm h we will take outside, and this outside will get cancelled with this norm h. So what I will have is as follows. So this is if and only if limit as h goes to 0 norm of, so this norm will get cancelled, so I will have f1 p plus h minus f1p minus t1p upon norm h, okay, comma f2 p plus h minus f2p minus 2p upon norm h, comma dot fm p plus h minus fmp minus tmp upon norm h. This bracket complete, norm h, this is equal to 0. So the limit of this norm is 0, that means the vector is 0, limit of vector is 0, so limit of h goes to 0. This is equivalent to saying that f1 p plus h minus f1p minus t1p upon norm h, comma f2 p plus h minus f2p minus t2p upon norm h, comma dot. The last vector will be fm p plus h minus fm p minus t1p upon norm h. This vector complete. This is equal to, I should write down this. This is equal to this is equal to 0 vector. Now it is not single 0, so it will be 0 vector because this is a tuple. So what what reason I should say, the reason for writing this, one should know this rule, that limit of norm f is equal to 0. If this is true, then limit of f must be 0. So this result one should, if the norm of function is 0, then the function must be, limit of a function must be 0. So this simple property I am using. Now limit of this entire tuple is 0, that means each and every tuple goes to 0. So this is equivalent to saying that if and only if limit of h goes to 0, so each vector is equal to 0. So I'll take the ith vector, specifically fi p plus h minus fi at p minus ti at h upon norm h. This is equal to 0 for all I goes from 1 to m. So this would imply, this is a differentiability definition of a scalar field. So this means that fi is differentiable at p. So this proof, converse part, you just need to go backtracking. If you go in a reverse way, you will get the converse. So hence I have, while writing, I have written an arrow in a both way. That means converse part is also 2. Now here one should further note that further here df at p is equal to capital T, which is equal to t1 t2 dot 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 tm, which is same as your derivative of f1 at p comma derivative of fm at p. So for each fi from Rn to R, now note that though each fi is from Rn to R, they are scalar field. We get, so since it is differentiable, so partial derivative exists. So we get dou fi upon dou xj at p exist for all j goes from, how many variable we have, 1 to n, x1 x2 xn, and we even know that t1 at e1 is nothing but dou f1 upon dou x1, because if you evaluate your linear transformation on a standard basis, you get a partial derivative. Similarly, t2 at e1 will give you dou f2 upon dou x1 dot 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 tm at e1 will give you dou fm upon dou x1. On similar line, we can write down t2 of e2, sorry, t1 at e1 e2, so it will be dou f1 upon dou x2. T2 at E2 will be dou F2 upon dou X2, so on and so forth. Tm at E2 is equal to dou Fm upon dou X2. So in continuing this way, we will have Tm, so Tm will be dou Fm upon Tm evaluated at En, so dou Fm upon dou Xn, Tm evaluated at En will be dou Fm upon just I should say not Tm, I should say T1 T2. T1 at En will be F1 evaluated at dou x by dou xn. Then here T2 that dou F2 upon dou xn, so on and so forth. So Tm evaluated at En will be dou Fm upon dou xn, and this can be return at this is evaluated at p, so this is all evaluated at p, that should be noted. So what I got is as follows. So I can say that T at E1 is basically T1 E1, T2 E2, dot Tm, sorry it is E1 only, Tm E1, which is same as dou f upon dou x1 at p, dou f upon dou x2 at p. This is f1, this is f2, dou f3 upon this, everywhere even it is, so I should write down it is because x1 only, then dou x1, this is at p, dou fm upon dou x1 at p. Similarly Te2 is equal to T1 E2, T2 E2, dot Tm E2, and we can even that write dou f1 upon dou x2 at p, dou f2 upon dou x2 at p, dot dou fm upon dou x2 at p. Right. So in general we can have T of En is equal to T1 En, T2 En dot Tm Em, so which is same as Tf 1 upon xn at p, dou f2 upon dou xn at p, dot dou fm upon dou xn at p. Okay, so if we write down this with a standard basis, matrix representation with a standard basis, so with respect to standard basis, matrix of T turns out to be that is matrix of T will turn out to be dou f1 dou x1 dou f1 dou x2 dou fn dou f1 dou xn, so dou f2 dou x1 dou f2 dou x2 dou f2 dou xn, dot dou fm dou x1 dou fm dou x2 dou fm dou xn at p. We have to evaluate at p, and this is basically our Jacobian matrix of f at p, right? So this Jacobian matrix we have already stated, so one should understand that the matrix representation is basically a Jacobian matrix. Okay, so after that there is a result that a differentiability implies continuity, so that I will prove. So f is from U subset of Rn to Rm, m greater than 1, U is open, set in Rn. If f is differentiable at p belongs to U, then f is continuous at p. So this is basically differentiability implies continuity. That result we are going to do. Okay, so proof. So it's given that f is differentiable at p. So this would imply by definition there exists a linear transformation T from Rn to Rm and an error function E from Rn to Rm such that f of p plus h minus f of p is equal to T of h plus U of h, where limit of E of h, norm of E of h upon norm h goes to 0. Okay, so we have to prove that f is continuous. To prove that f is continuous, so what I'll do, I'll consider this part, limit of this. So consider limit as h goes to 0, f of p plus h minus f of p. So if I could show that this limit is 0, implies that my function is continuous. So let's find out this. So limit as h goes to 0. So from star, let's call this a star. So from star, this is replaced, this can be replaced by T of h plus E of h from star, which is same as limit of h goes to 0 plus T of h plus limit of h goes to 0 E of h. So this here we can multiply and divide it by norm h, and if the norm of the limit goes to 0, then the function also goes to 0, that is if and only if. So this limit is 0, so this will goes to 0. So I left with only h goes to 0 T of h plus 0. But this T of h is also can be replaced by following, so which is same as limit h is basically h1 h2 dot 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 hn, that goes to 0 vector, basically 0 0 0. So T of h can be written as h1 e1 plus h2 e2 plus dot 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 hn en. You should know that h is equal to h1 h2 dot 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 hn. And now since T is a linear transformation, you can see that this is equivalent to saying that h1 h2 this all hn goes to 0 vector. So this is equivalent to saying that h1 T of e1 plus h2 T of e2. Use that T is linear transformation, hn T of en. So this limit will goes to 0 basically, because h1 to hn goes to 0. So ultimately what I got is as follows: limit as h goes to 0, f of p plus h minus f of p is equal to 0. So this would imply that limit of h goes to 0, f of p plus h minus limit h goes to 0, f of p is equal to 0. So this is same as limit h goes to 0, f of p plus h minus, this limit is f of p only because it is independent of h. So this would imply limit h goes to 0, f of p plus h, this minus f of p we can take on this side. So this would imply f is continuous at p. Well, this completes the proof of differentiability implies continuity. Well, I just wanted to remind one thing. Yesterday I have uploaded a lecture wherein the maximum and minima in a problem was, so I said that delta greater than 0, a greater than 0, then I said f has a maxima, so there is a correction, you should say f has minima. That one should note, everybody should note. Similarly, delta greater than 0, a less than 0 implies f has maxima, because it's a second derivative test. And third one is delta less than 0 implies saddle point. And the last one is if the delta is equal to 0, then test is inconclusive. We cannot determine anything about the maxima and minima. Well, we will explore a few more problems based on this, but timing this theory part, I wanted to cover 2 video lectures. So these theorems, both theorems are important. I have already done the addition of two differentiable function is differentiable and scalar multiplication is differentiable for vector valued function. So we'll upload the videos of that also soon. Thank you. Thank you for attending the lecture.